we're going to talk about trigonometric substitution. So let's talk about the motivation. Now, calculus is built off of geometry, and its goal is to answer application problems. And oftentimes, when we look at geometry, it's looking at things that involve distance. In fact, even the word geometry, if you think about where it comes from, the word geo, it means earth, like geography. And metry means measures, measuring the earth. And so it's really, from the start, mathematics has been about, let's do something practical. From the Pythagorean Theorem, we discover that one of the best ways to measure distance ends up involving square roots. So if I think I have a pair of points, say x0, y0, and x1, y1, I can say, what's the distance between those 2 points? Well, you draw a right triangle. You say that one side, which is measuring how you change in x, that's x1 minus x0. The other side, which measures how you change in y, it's y1 minus y0. And so the hypotenuse, which is the distance, the square root of x1 minus x0 squared plus y1 minus y0 squared. And now we see our challenge right here. The square root. The square root is a huge obstacle because, unfortunately, as much as we'd like it to be true, the square root of a squared plus b squared is not a plus b. And we've been saying this for hundreds of years. And for hundreds of years, calculus students have said, I don't think so. And they do it on their exam. And many points have been lost. We've used a lot of red ink on that type of answer. So unfortunately, it's not that simple. But we need to figure out a way to deal with it, because these are the type of problems that are going to arise in applications. How do you deal with the square root? And really, the challenge is not so much the square root. The real challenge lies in the following. This plus sign, that's where the real challenge lies. If there wasn't a plus inside that square root, we're okay, because something to a power we can usually handle. So what we want to do is find a way to remove that. Now here's the good news. The same place where our square roots are coming from, the Pythagorean Theorem, is going to be a way for us to get rid of square roots in some really nice cases. So we've written down some of the Pythagorean identities, and these are sometimes written in slightly different ways. So oftentimes we're thinking of sine squared plus cosine squared equals 1. But here we're rewriting it as 1 minus sine squared equals cosine squared. 1 plus tangent squared equals secant squared. But of course you can move the 1 across. Secant squared minus 1 equals tangent squared. Now why are these useful? Well, we can anticipate. See, what happens is, imagine we took the square roots. So we were to do that. So if we took the square root of one side, we take the square root of the other side. And we say, well, on the left-hand side, we have that pesky either plus or minus sitting there, which says it's hard to remove it. On the other side, there is no pesky plus or minus. You get something like the square root of cosine squared, which is cosine. Now, why do we put quotes and not say equals? Well, got to be careful. It is possible that the square root of cosine squared might be the absolute value of cosine. It just depends on where cosine ranges. Oftentimes, if we're doing an indefinite integral, we'll just say, don't worry about the absolute value. If we're doing a definite integral, we just do a quick check. So again, this holds for these other things. And lo and behold, what we see is that in these special cases, we can free ourselves from a square root. So now, with that idea in mind, we say, all right, we're going to do what's called trigonometric substitution, which says trigonometric things have a way to get rid of square roots in pesky situations. So what we're going to do is we're going to replace our variable that we're integrating with respect to with an appropriate trigonometric function. Now we have to think about, well, what's an appropriate trigonometric function? Well, it's one of the ones where we can plug it into one of those Pythagorean identities and life is good. That's the appropriate one. So here we go. If we see something like the square root of a squared minus u squared, what do? Well, the answer is we substitute u equals a sine theta. Why? Well, if you come back to what we just had before, see how we have the square root of 1 minus sine squared? What we want to do is we say, oh, this looks like 1 minus something squared. The a, okay, we can fix that. That's easy to fix. So I want to make it look like that Pythagorean identity. So when we substitute u equals a sine theta, we get our nice Pythagorean identity we can pull out. And so, lo and behold, it simplifies to a cosine theta. Again, most of the time we don't worry about the absolute values, only when definite integrals come into play. Square root of a squared plus u squared, well, that looks like the 1 plus tangent squared. So we say, well, I really want this to be like a tangent. So substitute it for tangent. U equals a tangent theta. Then the square root of a squared plus u squared equals a secant theta. And finally, u squared minus a squared. Well, I want to use my last one. That's secant squared minus 1. So I substitute secant. And if I do that, I get that the square root of u squared minus a squared is a tangent theta. So in particular, what we're doing here is we're setting ourselves up to help us get rid of square roots. That's the goal of trigonometric substitution. Now, I will say there's actually a bigger meta goal, but for right now I'm just going to say, think of it as it's helping us get rid of square roots. And when we get to our sort of bigger meta thing that it actually does, we'll point that out. That's coming up towards the end. Now a few things. Let's figure out how this all fits together. These are trigonometric functions, so we think of trigonometric functions in terms of triangles. So you should know, how do the trig functions relate as ratios of triangles? So sine is the opposite over the hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Now some people remember this with the, of course, the very familiar phrase, SOHCAHTOA. And if it helps you remember that silly nonsense word, then remember it. That's okay. See, if it helps you, it's not silly. The other thing, of course, is the secant, which needs to be the opposite of cosine. So you flip cosine, that's hypotenuse over adjacent. So I want to run through these substitutions because we're going to need to look at these triangles. They're going to come into play as we work through these problems. So when we make a substitution, u equals a sine theta, that's the same thing as saying sine of theta is u over a. Okay, well, what do? Well, the sine is the opposite over the hypotenuse. So if I draw a triangle and I put theta in the corner, the opposite is u, the hypotenuse is a. So I have u and a. So what's my missing side? Well, my missing side, by the Pythagorean Theorem, is the square root of a squared minus u squared. Now I want to point something out. I'm going to keep pointing this out several times. This piece here matches that piece there. That's not a coincidence. We're going to see this. Is when you draw the triangle, you're going to see, oh, that missing side, when I actually figure out what it is, it's the same piece that motivated my substitution in the beginning. And it happens consistently. If we set u equals a tangent to theta is u over a. So tangent is the opposite over adjacent. So the missing side is the square root of a squared plus u squared. And again, these match. U equals a secant theta. That says secant theta is u over a. Hypotenuse over adjacent. The missing side is the square root of u squared minus a squared. And again, they match. All right. So here we go. Let's start with some problems. So our general strategy. So if factoring or substitution has failed, don't forget, you still have all these old wonderful tools. Lots of times when you have something inside a square root, it'll happen that things factor nicely. Lots of times it won't. You have to check. So look for factoring, look for substitution. If those have failed, then we move to making an appropriate substitution. What's the right trig function? So it's good to know what happens in each one of the three cases. Now you make the trig substitution, and what's going to happen is you're going to transform your integral. Instead of being one that involves algebra, so like square roots of x squared minus 1 or something, it transforms into something involving trigonometry. So you're changing it from algebra land to trigonometry land. But the good news is we know how to handle things in our trigonometry land, or at the very least we have a lot of identities that allow us to make progress. And so we carry out the integral. Then at the end, we work backwards. And you want to be able to draw a triangle because in many cases you'll need the triangle to refer to figure out what certain trigonometric functions need to be. If you end up with just a theta by itself, for example, that will become an inverse trigonometric function. So here's an example to start off with. Find the integral from 0 to root 8 of the square root of y to the 4th plus y squared. Well, what do we do? Any suggestions? Could we substitute u equals y squared? Well, maybe. Now, this came from an old final exam, I believe. So, it's good for us to be able to answer this. Now, here's the great news. We don't need Calc 2 to answer this one. This is a Calc 1 type problem. That's not so obvious. So remember, we don't rush into trig substitution until we check what? Well, is there something that factors nicely? Or is there something for substitution? Y to the 4th plus y squared, what can we do to that? Yeah, you can factor out a y squared, right? So 0 to root 8 square root of y squared times y squared plus 1. Now what can you do? Well, square root of y squared plus 1 you can't do much. What about square root of y squared? Well, you're asking me why because we want to make progress. No. Yeah, square root of y squared just becomes y. Right? Yes, it does. So 0 to root 8 of y square root of y squared plus 1 dy. So one of the things we have in our mind when we're doing integration is our philosophy is let's try to make things look simpler. Because simpler things are simpler. And we have a better chance. So a lot of integration comes down to saying, how can you rewrite things so at least it's a little bit more palatable? What can we do here? Substitution. What's our substitution to make? Oh, we could do tangent. Wow, you guys really want to do trig substitution. You're just like, I'm fired up. Send me in, coach. Send me in. How about u equals y squared plus 1? What would du be? 2y dy, right? And notice, what do we have? A y dy. So you're like, aha, Steve, see, it's going to fail because there's no 2. Okay, now there is. But we got to compensate, so we'll throw in a half. All right, so what does this become? Well, now we see we can rewrite this. There's a half integral. The 2y dy becomes our du. Square root of y squared plus 1 becomes u to the 1/2. Where do we go from? What are our new bounds? 9 is the upstairs one because square root of 8 squared plus 1 will be 9. How about downstairs? 1. Because 0 squared plus 1 is 1. And from here, we finish it off. We have the 1/2. Take u. What's our new power? 3/2. Multiply in front by the reciprocal, which is 2/3. The 2's cancel. From 1 to 9. And we end up with 1/3. Then we have 9 to the 3/2. 9 to the 3/2. Well, you could say, let's take 9, cube it, that's 729. Square root of 729 is, of course, is it? I think it's 27. Here's an easy way to do it. Instead of cubing it and then taking it to the 1/2, take it first to the half. 9 to the half is 3. 3 cubed is 27. 1 to the 3/2 is 1. That's the nice thing about 1. 1 to any power is 1. So we end up with 26 over 3. All right, so this problem is not one involving trig substitution. It's just as a reminder, don't give up on the old ways. The old ways are good ways. And we shouldn't just jump in and say, hey, I'm going to replace you with my shiny new toy. No, no, no. Use all the tools you have available. All right, so here we go. Find the integral square root of 1 minus x squared dx. We've been doing this integral a fair amount. Definitely at the end of Calc 1 we used it a lot. A couple times at the beginning of Calc 1 we've used it. Sorry, Calc 2 we've used it. But whenever we've used it, it's always been a definite integral. And then we said, ha-ha, it's a circle. Now it's not a definite integral, which means, aha, it's not a circle anymore. So it means we have to figure out how to find what is the antiderivative. All right, so in this format, square root of 1 minus x squared, what's our substitution to make? Yeah, so if you come here, it's the square root of 1 minus something squared. That's our variable. So that says a is 1, so it's 1 minus x squared. So u, our substitution, in this case our variable u is, we're calling it x, so x should be sine theta. All right, so here's our substitution. X equals sine theta. Now remember, whenever you do a substitution, you always have to update everything. So we're going to have to update this part, and we're going to have to update that part. So we say, okay, what is dx? Derivative of sine theta? Cosine theta. d theta. Now, the square root of 1 minus x squared. Well, that's the square root of 1 minus sine squared. Well, that is square root of cosine squared, which we'll just assume to be cosine. When it's an indefinite integral, we don't worry about absolute value issues. So what do we get? Well, we get that this integral, square root of 1 minus x squared dx, is going to become the integral of cosine theta from the square root of 1 minus x squared. Then dx is going to become cosine theta d theta. So that's our integral. Now, if we clean this up, we see, aha, this is also known as cosine squared. So how do you integrate cosine squared? Is there a way to do that? From what we talked about last time. Power reduction. Power reduction, because it's an even exponent. When you have an even exponent, you've got to bring down the powers. Okay, so what is cosine squared equal to? There's 1, there's a cosine 2 theta, there's a 2. Is it a plus or minus in the middle? It's a plus. Now, one way you can remember, I don't know if it's necessarily the easiest way to remember, if you're not sure, you can think about, it has to be true when theta equals 0. Cosine squared of 0 is 1. So if I put in the plus, I'll get that 1 equals 1. If I put in the minus, I'll get 1 equals 0, which is false. So it needs to be the plus if it has any chance of being true. So now we're in good shape. The integral of 1/2. So the integral of 1/2. A half theta. And then the integral of, cover up the 1, integral of cosine 2 theta over 2. What is that? One over something, 1/4 sine of 2 theta. Anything else? Plus c. Because we want the points. All right. Are we done? No, we're not done. Well, what do we need to do? Well, what we need to do is get everything back in terms of x. Now, the first part, there's theta. Well, to get theta, I come back and say, well, I know that x equals sine theta, so I want to get the theta outside of the sine, so we can say that theta is arcsine of x. So that frees up the theta. So this is going to be 1/2 arcsine of x plus, now we have to think about sine 2 theta. Now here's the challenge with sine of 2 theta. It's the 2 in the inside. Because we know what sine theta is, but we don't know what sine 2 theta is. In particular, we know that sine theta is equal to x. So how can I make sine 2 theta look like sine of theta? It's almost like I have double the angle I want. How do I handle something like that? Is there anything that works with a doubled angle? Maybe an identity of sorts? What? Oh yeah, there's this identity, the double angle identity, which allows us to say that sine of 2 theta is the same as 2 sine theta cosine theta. So, if we do end up with something on the inside, we can use double angle identities to sort of get back into sine theta and cosine theta. All right, well, 1/4 times 2, that's 1/2. Okay, that's good enough. What do we do about the sine theta? What does that become? X, because we said it right here. X equals sine theta. What about cosine theta? All right, well, you can do 2 things. One is you can say, we have it right there. It says cosine theta is the square root of 1 minus x squared. Okay. So that would be it. And now you're thinking, Steve, that was one thing. What's the other thing? All right. So the other thing, we can get away with it because in this case it ended up being already present. It won't always be the case. The other thing is to say, well, let's look at this sine theta equals x. We'll do it in this little corner up here. So if I'm saying that sine of theta equals x, I can also think of a sine of theta as x over 1. So I draw a triangle, I put theta. I say, all right, sine is the opposite over hypotenuse. I figure out the missing side by the Pythagorean theorem. What will the missing side be? Square root of 1 minus x squared. And now, notice that this matches with that. So the square root piece, that's the part motivating our substitution, matches with that missing side. So finally, if I want cosine theta, it's the adjacent over the hypotenuse, which is square root of 1 minus x squared. So that's the other way to do it. And that's the answer. All right, that's not so bad. We could have done that back in Calc 1. Well, maybe. We actually did. We actually did, if you go back and look at your notes. All right, let's do a lot more. The more we do, the better we get. Find the integral of dt over the square root of 9 plus t squared. All right, I don't know what that looks like. It's something. What kind of substitution are we going to make here? Looking back on our list, which one are we in? We're in the middle one, right? We're here, square root of a squared plus u squared. So in our case, when I look at that 9, what should I really be thinking? I should really be thinking of that as 3 squared. So here, we get that the t matches up with the u, 3 matches up with a, so our substitution will be 3 tangent theta. All right. So we'll let t be equal to 3 tangent theta. What's dt going to be? Three secant squared d theta. All right, well, we need to do something else. Let's figure out what is the square root of 9 plus t squared. Well, according to this, That's the square root of 9 plus 3 tangent theta squared. Well, that's the square root of 9 plus 9 tangent squared theta. What can we do here? We can pull out the 9, because that's common. So now we see why we need that a. So why did we need to put that 3 there? We needed that 3 there because I wanted to pull out, so the 9, so this becomes 3 square root of 1 plus tangent squared. 1 plus tangent squared, also known as secant squared, and therefore we get this as 3 secant theta. Now oftentimes that step is automatic, we don't even have to do a lot of work. Okay, from here we're ready to carry out our substitution because we know what to do, because we have the dt, we know what that's going to become in terms of theta, and we have the square root of 9 plus t squared, we know what that's going to become. So we get that this is equal to the, all right, so the integral of dt divided by the square root of 9 plus t squared is going to become, upstairs we're going to get 3 secant squared theta d theta. Downstairs we're going to get 3 secant theta. Now, what do we do here? What do we have as an option? Well, the 3's cancel. Anything else? Yeah, I get a secant to cancel, so we're left with the integral of secant. Now, how do you integrate secant? Yeah, the way you integrate secant is you memorize it. It's one of the 10 that you need to know. And remember, there's just 10 of them. So you should know them. So log of secant plus tangent. And then plus c. All right, are we done? We're never done? Oh, that makes you sound a little bit pessimistic. Be optimistic. All right. Well, right, we need a little bit more work. So we need to figure out what do we do with secant and what do we do with tangent. Now, we don't have to draw a triangle in this case. We actually have enough to figure out from here. Do you want to draw a triangle? Do you not want to skip that step here? Yeah, draw the triangle. Okay. Triangle in the corner. So tangent theta. If I come back to our original substitution, I can say that tangent of theta is equal to t divided by 3. So when we draw our triangle, theta is in the corner. And then we have that the opposite side is t, and the adjacent side is 3. So what's the hypotenuse? Well, it would be the square root of 9 plus t squared. And again, see how that square root of 9 plus t squared matches with this? If they didn't match, you should be suspicious and say, oops, I made a mistake. Let me go back and try again. All right. But they do match. So now we can say what? Well, we can say secant is what? Secant is the hypotenuse over the adjacent. So that's natural log of the square root of 9 plus t squared over 3. What's tangent? Tangent is opposite over adjacent. T over 3. And then plus c. All right, so that's the answer. Now, if you punch it into your calculator might say, hey, that's not the answer. This is the answer. Log of square root of 9 plus t squared plus t plus c. All right, who's right? Us or the calculator? We're both right. Now you might say, but how is it possible that these are both right? Can you see why these are both equivalent answers? There's a little bit of misdirection going on here. The misdirection is the c's. Do these c's have to be the same? No, they don't have to be the same. Now notice, in the first case here, what could we have done? You could have written this as log of square root of 9 plus t squared plus t over 3. Common denominator of 3. Now what happens when you have a log of something over something? It becomes subtraction. So this can become log of square root of 9 plus t squared plus t minus log of 3 plus c. Well, but what kind of thing is log of 3? It's a constant. And constants are pretty good at absorbing constants. So this becomes a bigger uber c, a larger c, if you will. And so it absorbed a constant. Now, you'll get full credit for either answer. I just want you to be aware of sometimes people do manipulations, and so you have to be aware that things can happen. All right. Well, let's try another one. Integral of dx over x to the fourth times the square root of x squared minus 1. Okay. Well, I bet you I know what kind of substitution we're going to make. Because we've already done one that involves sine, and we've already done one that involves tangent. So by process of we need to do all of them, it probably should be the secant one. And it is the secant one, because it's something squared minus a number. And so when you see that, when it's minus the number, that's the secant one. All right, so here we go. Let's put a little dividing line. So we're going to have x equals secant theta. What does dx become? Secant tangent. Then we throw on a d theta on the end. Square root of x squared minus 1. That's going to be the square root of secant squared minus 1. Secant squared minus 1. Tangent squared. So we are setting it up so that we can get rid of that square root. Lo and behold, it becomes tangent. Just like we'd like. So our integral, dx over x to the fourth square root of x squared minus 1. The top, secant theta, tangent theta, d theta. Downstairs, x to the fourth will become what? Secant to the fourth. Square root of x squared minus 1 will become tangent. Now, what can we do? We can do some cancellation. What cancels? Tangents cancel. Anything else? One secant cancels. So this becomes secant cubed downstairs. All right. How do you integrate 1 over secant cubed? Okay, so yeah. So the answer is we don't integrate 1 over secant cubed. We rewrite it. So 1 over secant cubed is the same as cosine cubed. Ooh, that looks nice. Now, how do you integrate cosine cubed? Now here, it's cosine to an odd power. We like odd powers, because that means we don't need power reduction. So what do we do when there's an odd power? Do you remember last time? I know it was a long time ago. So when there's an odd power, the idea is pull one term off on the end. And now, what's going to be left? Well, right now it's cosine squared. But what's our goal? Our goal is to say, make this cosine. So make this become sine theta stuff. In other words, we want to replace everything in terms of sine, because we're setting ourselves up for a good substitution. What can I do to replace that cosine squared theta so it looks like stuff that involves sine? Yeah, cosine squared is 1 minus sine squared. And now I can do our substitution. U equals sine theta. And at this point, you're probably wondering, are you allowed to keep doing substitutions? Absolutely. Every time you're doing an integral problem, each layer say, look, let me start as if this was a fresh integral and I didn't know where it came from. What do I do right now? What does du become? Cosine theta d theta. So, what do we get? We get the integral 1 minus u squared du. Okay, that's an integral we can handle. So what is the integral of 1 minus u squared du? U minus 1/3 u cubed plus c. Now we start to unravel our substitutions. First thing, go back one layer. What do we do with u? It becomes sine. So this is sine theta minus 1/3. I'll write it as sine theta cubed. Are we done? No, we got to keep going back. Now here, we actually do need the triangle because it's not clear what sine theta should be. So let's put our triangle up. We'll do it here in our corner. So we have that secant of theta is x, and since there's not a ratio, I'll make it a ratio by saying it's x over 1. So there's our ratio. We draw our triangle, trying to make it look like a right triangle. In terms of the triangle, what's the ratio for secant? What does it correspond with? Hypotenuse over adjacent. So I think of the ratio hypotenuse over adjacent. So hypotenuse is x, adjacent is 1. What's my missing side? Well, it's going to be square root of x squared minus 1. Because this squared plus that squared equals x squared. So 1 plus whatever this squared is equals x squared. So you subtract and take the square root. It matches with what motivated the substitution. Now, we say, okay, what's sine of theta? Well, sine of theta is, as a ratio, what is sine of theta? Opposite over hypotenuse. So the opposite, square root of x squared minus 1, hypotenuse is x. So we get the square root of x squared minus 1 over x minus 1/3 square root of x squared minus 1 over x cubed plus c. This is one I don't think we could have guessed. Well, the nice thing is we don't have to guess. We have something that's more systematic. We can do the math. We can solve the problem. All right. Well, let's try another one. Find the integral from -1 to 0 of dy divided by y squared plus 2y plus 2 quantity squared. Now, when you look at this problem, trig substitution is probably not the first thing that comes to mind. Because the way we oftentimes think about trig substitution is, let's get rid of the square root. That's our goal with trig substitution. And when you see this, what don't you see? You don't see a square root. So why do we throw this up on trig substitution day? This problem will be a trig substitution problem. And here's the thing. It's not necessarily that trig substitution is used to get rid of square roots. The real goal of trig substitution is to get rid of that plus or minus sign in the middle. And that's what we can do. And we'll see that by making a good substitution, if we can get rid of the plus or minus sign, life is happy. Of course, that's not surprising. It's a beautiful day. Life is always happy. So, y squared plus 2y plus 2. It's not so obvious what we need to do, because in general, I see the y squared, but I need to have my form be something like u squared plus a squared, or it has to be u squared minus a squared, or it has to be a squared minus u squared. These are the three forms we have. The thing is, there's a y there and a y there. That messes us up. We want to only have like a single variable. So we need to figure out a way to handle that as well. All right, so what's our thought process? Well, notice, what do we like? We like squares. Those are squares. So, what should we be thinking of doing? We should be thinking of, let's make things look like squares. Is there any way that we can make things that aren't squares, complete them somehow to make them squares? What's the process called? To complete the square. Right. Good. Okay. All right. I was worried I was being too subtle. Okay. Good. Okay. So, integral (-1 to 0 dy). So I say, okay, I have the y squared plus 2y. I want to add something so that this thing would be a square. What do I add here to make it a nice square? You'd add 1. So the rule is, assuming that what's in front of your y squared is a 1 coefficient, take the middle term, divide by 2, square it, and that's what you add. So if you did that, you get y plus 1 quantity squared. Now notice, we have y squared plus 2y plus 2. We've only added plus 1, which means we still have a plus 1 left over. So the denominator really looks like y plus 1 quantity squared plus 1. All right. So we have integral (-1 to 0 dy over y plus 1 squared plus 1 squared. So now we're a little bit happier. So it's of the form something squared plus something squared. Because notice, true fact, 1 is equal to 1 squared. Yep, I learned that a long time ago. It's come in very handy many times in my life. Okay, so that says this y plus 1, that's what's going to act as our u. So what does y plus 1, that's our u, what should we set that equal to? Yeah, this is a tangent substitution. So y plus 1 should equal tangent theta. You're absolutely allowed to do this kind of manipulation. There's no problems here. What does dy become? Think of taking the derivative of this side, it's dy. Derivative of this side, secant squared. And we should talk about, what does y plus 1 quantity squared plus 1 become? Well, that's tangent squared plus 1, which is secant squared. So what do we get? We get the integral of dy is secant squared theta, d theta. Downstairs, we're going to get secant squared theta squared. What else do we need to do? Are we done? The bounds. This is a definite integral. When you have a definite integral, you need to update the bounds. So, let's talk about our bounds. At y equals -1. Well, we'll get that 0 equals tangent theta. What angle, when we take the tangent of it, gives us 0? 0. So that says our lower bound at y equals -1 becomes theta equals 0. At y equals 0, so plugging y equals 0 into our relationship, we get that 1 equals tangent theta. What angle, when we take the tangent of it, gives us 1? Pi over 4. Now, here's the nice thing, is once we update the bounds, we never have to go back. We never have to go back to y at the end. From here on out, we just carry out the integral. So it's a trig integral from here on out. We never go back. What can we do to simplify secant squared over secant squared squared? You can certainly cancel a single secant squared, and then it becomes cosine squared. So at this point, this is not too surprising, and since we're short on time, I'll just talk about this while the pen magically writes down the answer. So we did what we did before, namely we do our power reduction. Cosine squared is 1 plus cosine 2 theta over 2, which makes this 1/2 theta plus 1/4 sine of 2 theta, which hopefully we remember all that because we just did this a little while ago. It's a definite integral, so we don't need the plus c, but we do need to evaluate. So we're going to go from 0 to pi fourths. 1/2 times pi fourths, well, that would be pi over 8, plus 1/4 times sine of 2 times pi fourths. Well, 2 times pi fourths is pi halves. Sine of pi halves is 1. So we get plus 1/4. And when you plug in 0, you'll get 0 and sine of 0, which is 0, which means those parts cancel, and you get pi over 8 plus 1 over 4. So trig substitution does work here as well. Okay, let's try another problem. This will have a little bit of similarity to what we just did. Find the integral of the square root of 21 plus 4x minus x squared divided by x minus 2. So we're back to our square root. That's good. We like that. Something we're more comfortable with, at least when we're thinking about doing our trig substitution. And now we say we have sort of the same situation going on. We need to complete the square. So let's think about how we can rewrite this. Now, whenever you're completing the square part, you want to be that in the front. But the other thing is you want that to have a coefficient of 1. So I'm going to start by rewriting this as minus, then I'm going to put a parenthesis, x squared. Now the next term, 4x, well, I'm going to write that as a minus 4x, right? Because minus minus makes plus 4x. And now comes the question. I have x squared minus 4x. What do I need to complete the square? In other words, make it a perfect square. Take the middle term, divide by 2, square it. You'd need to add 4. Now that's a perfect square. I'm going to put a parenthesis here. Now I have to be careful. I have here what? Minus 4. I need to end with 21. So minus 4 plus what gives 21? The answer is 25. Minus 4 plus 25 is 21. And downstairs we have x minus 2. All right. So if we rewrite this, we can say this is the integral. Now I'll put this back in the order that we would normally see this in. Now that I've handled completing the square, 25 minus, and this was chosen to be a perfect square, it's x minus 2 squared. Now the good news is, notice this x minus 2 matches with that x minus 2. I don't think that's a coincidence. I think it was planned that way. Now what's our form? Our form is we have the square root of 25 minus x minus 2 squared. So that's our square root of a squared minus u squared. So here we get that a is 5 squared, and u is x minus 2. What's the right kind of substitution to make? A squared minus u squared, that's sine. So our substitution would normally be u equals a sine theta. So if we do that, we get that x minus 2 is 5 sine theta. So there's our substitution that we want to carry out. All right. Now, let's see where this goes. If x minus 2 is 5 sine theta, what are we going to get? Well, the square root of 25 minus x minus 2 squared, that's the square root of 25 minus 25 sine squared theta. You can pull out the 25, so we get 5 square root of 1 minus sine squared. See, we wrote it, so we get that Pythagorean thing going. That's 5 square root of cosine squared, or 5 times cosine. Okay. And, well, what else do we have? Well, we have dx. We haven't done that yet. So dx would be derivative of 5 sine theta is 5 cosine theta d theta. All right, that's promising. And let's see, anything else that we need to say? No, I think we have everything. We can take care of the x minus 2. We can take care of the square root of 25 minus x minus 2 squared. We can take care of the dx. So this is going to become equal to the integral. This square root is 5 cosine theta. And now the dx is what? Well, the dx is another 5 cosine theta. And then the x minus 2 is 5 sine theta. And we're integrating that d theta. All right. Interesting. Well, what can we do? What can we do? Now, this is actually not so bad. There are things that we can do. So here's one thing we can do to finish up. First off, we can cancel off a 5. And then we have a 5 left over. All right, so the 5 comes out. Cosine times cosine, that's cosine squared. And cosine squared is 1 minus sine squared. So 1 minus sine squared theta over sine theta, d theta, which would end up giving us 5 times the integral of 1 over sine minus sine squared over sine. So that's sine. Well, that's 5 integral cosecant. Well, what's that? Well, we'll talk about that in a second. Minus sine. Now here's the thing. The question is, do we remember the derivative of, the antiderivative of cosecant? Well, we actually never talked about it. I'll make some notes to the side here. The integral of cosecant theta, d theta, is minus natural log cosecant plus cotangent. Now, where does that come from? Well, the derivative of cosecant, that's minus cosecant cotangent. Derivative of cotangent is minus cosecant squared, and then you work it out. So we could, of course, finish this up by saying, hey, this is 5 times minus natural log cosecant plus cotangent, and then minus sine, the integral of minus sine is plus cosine, then plus c. And dot, dot, dot. Now you might notice, Steve's not going very far with this one. That's a signal that maybe there's another way. And there is. You see, we kind of left out a detail, because I want to point something out. This square root of a squared minus u squared, where is it coming from that u equals a sine theta? Well, what's happened here is that our motivation for u equals a sine theta came from the following fact, that namely the square root of 1 minus sine squared is equal to cosine. So that's what motivated us, was that fact. But we also have that the square root of 1 minus cosine squared is equal to sine. Now, what's the point? So that says when you have the square root of a squared minus u squared, you really have a choice. You can either let u equals a sine theta, or you can let u equal a cosine theta. Now, why do we always point to this one first? And I'll tell you my personal opinion. The reason I think we point to this one first is when you take the derivative of this one, you get a positive cosine. But when you take the derivative of that one, you get a negative sine. So that negative is what biases us towards the sine. Now, what happens if we switch? Well, generally speaking, the process stays the same. But what will happen is oftentimes you'll switch. So your functions will become cos. So see how right now we have a cosecant we don't like cosecant, but secant we know. Sine could become cosine. So let's try this. Let's try our other form of substitution, and let's see where we get to. So we just need to grab a piece of paper. Let's see. We have a piece of paper over here. Come on, piece of paper. Come on. It's your big day. Here we go. All right. So here we go. We're going to come to here, and we're going to make a different substitution, and let's see what happens. So we're going to make the substitution. U equals a cosine theta, right? So that means our x minus 2 is 5 cosine theta. Now, that tells us that the square root of 25 minus x minus 2 quantity squared will equal, you skip a few steps, they're the same process. What will come out is 5 sine theta. And the other thing that will happen is that dx will be minus 5 sine theta d theta. So, what does our integral become? So our integral becomes integral of the square root 20, sorry, I was copying down. We're not copying, we're substituting. So the square root becomes 5 sine theta. The dx becomes minus 5 sine theta, that would be a d theta, and the x minus 2 becomes 5 cosine theta. Well, the 5's cancel. That's good. Like before, we can pull a 5 out. We have the integral of minus sine squared theta over cosine theta d theta. But now we say, well, what's true about minus sine squared? Well, sine squared plus cosine squared equals 1. So if I swap the sine squared into 1, we'll get that cosine squared minus 1 equals minus sine squared. So this becomes 5 times the integral cosine squared minus 1 over cosine. Cosine squared over cosine, that's simply going to be cosine, and 1 over cosine is secant. Okay, we haven't integrated yet. And now let's pause and compare. See how we have this one? It's 5, still stays the same. And now instead of sine, it's cosine. Instead of cosecant, it's secant. So essentially we swap the cos. So it can be the case that maybe you might want to try a different trig substitution, because there's always 2 variations that come into play. All right, it doesn't happen all the time, but from time to time. And how do you know when? Look if you're encountering cosecants. That's a sign. That's a sign that you should switch. So now we can integrate. So what do we have? We have 5, and then we have sine, that's the integral of cosine, minus natural log of secant plus tangent, and plus c. So now we come and draw our picture. So here's theta. We can say that cosine of theta is x minus 2 over 5. So cosine adjacent over hypotenuse. The missing side, you can probably guess, well, we would take the hypotenuse squared and subtract that squared. So that's the square root of 25 minus x minus 2 squared, which, by the way, if you clean it up, that's 21 plus 4x minus x squared. If that sounds familiar, that's because that's what we started with. So it should be familiar. So we're almost there. So what do we have? We have 5 times sine of theta. Sine of theta is opposite over hypotenuse. So square root 21 plus 4x minus x squared over 5. Minus 5 times the natural log secant. Well, secant is going to be the hypotenuse over the adjacent. So that's 5 over x minus 2 plus tangent is opposite over adjacent. So that's square root 21 plus 4x minus x squared over x minus 2, and then plus c. And we can cancel the 5. So we get a final answer of the square root of 21 plus 4x minus x squared minus 5 times the natural log 5 over x minus 2 plus square root of 21 plus 4x minus x squared over x minus 2 plus c. And that's our answer. All right. Well, that one's a challenging one. I think what makes this one challenging, there's a couple of things. There's the completing the square and recognizing there could be other substitutions to make. So keep your eye out. There's always sort of other options. So be open to those other possibilities that might be out there. All right, let's do another one. Find the integral dt over 2t minus t squared to the 3/2. Now you might say, oh, this kind of looks like one of the ones we did at the very beginning, where we're like, ha, there is no trig substitution. Well, actually, this one, it is a trig substitution problem. So there's no secret. Well, the big difference was we had t squared and t to the 4th. Now what can we do? Well, we can do the same thing we were doing before, namely practicing on completing the square. You might be like, wow, completing the square, really powerful. Yes, it is. You should learn how to do it. It'll save you points. And we like saving points. So minus t squared minus 2t. And now, what do we need to do? Well, to make this a perfect square, what we do, take the minus 2 divided by 2, square plus 1. And so that'll become t minus 1 squared. But be careful, there's a minus 1, so we need to also add 1. So that makes it so it's exactly as it was before, at least it will when we put to the 3/2 power. So we have that this is the integral dt over 1 minus t minus 1 squared to the 3/2 power. Now from here, we're saying, okay, good. This is what? Well, it's a number squared minus variable squared. So this is another sign. So again, we always go with the sign first. We only reach for a cosine if sine leads to some strange integrals that we don't like involving cosecants and cotangents. So t minus 1 equals sine theta. Then that says dt is going to be cosine theta, d theta. And let's see, what else do we get? Well, we also get that if we take the square root of 1 minus t minus 1 squared, well, that's equal to the square root of 1 minus sine squared, which is cosine. So we now have that this is the following. The integral, the dt, becomes cosine theta d theta. That's easy enough. Downstairs, we have 1 minus t minus 1 squared to the 3/2. So that's like taking the square root cubed. So the square root is cosine. So what we have is cosine cubed. All right, well, that's not so bad. What can you do? Well, first off, we can cancel a single cosine. So it's 1 over cosine squared. And we say, hey, 1 over cosine squared, that's nice. That's secant squared. Do we know how to integrate secant squared? Yeah, that's tangent plus some constant c. So now we just have to figure out what's tangent. Well, we could figure it out. Actually, we could do it from here, sine over cosine. So it's going to be these two terms. But let's suppose we didn't know that. Practice drawing our triangles. So remember, sine theta is t minus 1. Since it's not a ratio, make it a ratio over 1. And we draw our triangle. There we go. Put the theta in the corner. And it's the opposite over the hypotenuse. So the missing side, well, that'll be what happens when you take the hypotenuse squared minus the opposite squared. So 1 minus t minus 1 squared. And if you multiply that out, simplify it, that becomes square root of 2t minus t squared. Way back what we started with. So, what's tangent? Tangent is opposite over adjacent. So t minus 1 divided by the square root 2t minus t squared plus c. And we're done with that one. All right, that one was kind of fun. Good, good. I kind of think that one might be a little bit easier than the last one. Okay, one final one. This one should have us thinking for a little bit. And I like this. It's good to think. Find the integral cosine of z over the square root of 3 plus cosine squared z dz. Now, when we look at it, we don't think, this is not trig substitution. This looks like an integral which already has trig in it. So, I wonder why we're seeing it right now. Well, let's keep looking at it. Now, here's the thing. Whenever you see something involving sines and cosines, what do we like? Well, we really want to have something like this. We want to have either stuff with sine times a single cosine, or we want to have stuff with cosine times a single sine, right? Because if we are in either of these forms, there's an easy substitution to make. Notice we have a single cosine here. So this is suggestive. It's saying, you know, we could rewrite this as 1 over the square root of 3 plus cosine squared z times sine z, cosine z. I can copy. I learned to do that back when I was a kid. Times cosine z dz. Okay? Yeah, that's fine. Now, this would be great. It fits this form if this part, we can make it look like stuff with sine. And here's the thing. Cosine squared is more or less sine squared, because we have that identity. So we say, hey, this is equal to the integral 1 over the square root of 3. And what is cosine squared? It's 1 minus sine squared. Well, I didn't say cosine squared was exactly sine squared, but it's basically sine squared. Throw in some constants. And now we're in that happy place. It's stuff that involves sine with a single cosine. So now we say make a substitution. What's the substitution to make? Our substitution is we're going to let u equal sine of z. Then du will become cosine of z dz. All right? So what happens? Well, this part on the end, that's going to become our du. This part becomes what? Well, we have 1 over 3 plus 1 is 4, so square root of 4 minus sine squared, minus u squared, and then du. All right, so that looks a little bit simpler. And now we think to ourselves, okay, what do we do? And remember that rule. It says, when you're doing integration, whenever you have a new form, forget where you came from and ask yourself the question, can I do something with this integral? So regardless of the fact that there was trig here, I'm not going to worry about that. My question is, can I do something there? Is there something to do? And the answer is there is something we can do. This is of the right form. A squared, if we were to have 2 squared minus u squared. So, even though it sounds strange, we started with trig, we got to an algebra, now we're going to go back and do a trig substitution. Because the new integral says, hey, if you are smart, here's the right substitution to make. U should equal 2 sine theta. All right, so there we go. That's our substitution. What do we get? Well, we get that du is 2 cosine theta d theta, and square root of 4 minus u squared, well, that's the square root of 4 minus 4 sine squared, which is the 2 can come out, square root of 1 minus sine squared. So that's 2 times square root of cosine squared, which is 2 cosine, which is why we do our substitution. And what do we see now? Once we carry that trig substitution out, the numerator has the du. So that becomes 2 cosine theta, d theta. The denominator, square root of 4 minus u squared, becomes 2 cosine theta, which tells us that we're just integrating d theta. And now you'll agree that we started with this integral. This was simpler, but this, wow, really, you can't get simpler. Amazing, amazing, so good we can integrate. That's theta plus c. Now that's not our answer. We've got to work our way back. So let's go up, figure out where did theta come from. Theta came from this substitution. So we get that sine of theta is u over 2. And so to get theta, we got to get rid of the sine, which means use the inverse function. So theta is arc sine of u over 2. All right, good. So update. Arc sine of u over 2 plus c. Now, are we done? No, because our problem didn't start with u, it started with z. Okay, so now we got to go back and say, well, what was u? That's from here. U is sine z. So we get that this is arc sine of z over 2 plus c. And now we are done. And you might think, well, wait a second, don't arc sine and sine cancel out? Well, they would if there was no over 2, but because of the over 2, it changes the answer. So it's not quite the same. But there you go. That's the answer. And it's actually not so bad. It's kind of beautiful. But we're doing math, so lots of things are beautiful. All right, well, that's it for this session. But make sure you come back, because there's some good stuff coming up in the near future. All right, bye.